Okay, so now we've got all our lemmas lined up, we're ready to prove that the complement of a ball is acyclic. So here was the theorem, proposition, whatever. So let's say it this way. Suppose we've got some so we've got some continuous injective map from 0, 1 over k to Sn. So this means that the image is homomorphic to 0, 1 over k. Here we're using something here. I mean, this is a compact space, and Sn is Hausdorff. So I mean, this F, because it's injective, it gives you a continuous bijection from 0, 1 to the k to the image, and then that's continuous bijection, compact to Hausdorff, so it's homomorph. Okay. So then, anyway, the claim is that Sn with the image of F removed is acyclic. So as we mentioned before, we're going to organize this inductively for so we start in the case k equals 0, then the set that we're removing is just a single point. So the complement is complement is going to be homomorphic by stereographic projection to Rn. So complement to is contractible, and therefore it's like okay. And then for k greater than 0, we can assume the k minus 1 case inductively. Okay. Let's suppose for a contradiction that we've got some class in the homology of this complement. Okay, so case m bigger than 0, you get a contradiction if there's any non-zero class at all. For m equals 0, for contradiction, we have to assume there's a class in the kernel of P that's that's non-zero. Okay. Okay. So. Okay. So. So we're going to define some slices xj of width 2 to the minus j recursively. Okay, so our x naught is the full set x that we started with, just the image of the whole cube. Okay, so so by previous lemma, yeah, well, we'll choose these in such a way that the image, or of U, this class that we had here, this class U, in HM Sn less Xj is non-zero. So suppose we've already, how do we do this? We've already chosen Xj. So you split it in the obvious way. You split it in the middle into two slices of half the width. So Xj plus intersect Xj minus is a slice width naught, and therefore has a cyclic complement by induction hypothesis. Okay, we're assuming inductively that the complement of any k minus 1 cube is acyclic, and this intersection here, that's a slice of width 0, which means it's a k minus 1 cube, so it's got a cyclic complement. So our lemma that we had in the last video, okay, so in the last video, we had a y and a z, and we assumed the complement of y intersect z was acyclic, and we assumed that we had a non-zero class in the complement of y union z, and then the conclusion was that it had non-zero image either in complement of y or the complement of z. So here we're taking y to be xj plus and z to be xj minus, and by applying that, we get this conclusion here. So that just means we can take xj plus 1 is xj plus or xj minus as appropriate. Okay. If we've got a non-zero image in the complement of xj plus, then we use xj plus, otherwise we use xj minus. Okay, so now okay, so remember, so each of these guys, each of these xj's is a slice of width 2 to the minus j, and they're nested inside each other. And so if we take their intersection, then you're just going to end up with a single slice of width 0. So that means that the Sn less x infinity is acyclic. So that means that U goes to 0 in the nth homology of Sn less x infinity. So m is bigger than 0. This is kind of automatic because the group is just trivial. If m is equal to 0, then we know that h0 of Sn less x infinity is z. But because we assumed at the beginning that p star is 0 is 0, then that would mean that u has to go to 0 here as well. but remember, x infinity is the intersection of the xj's, which means that the complement is the union of the complement of the xj's, these Sn plus xj's, and each of these guys is compact, so it's closed, and so each of these is open. So that means that U has got U goes to 0 when we go all the way to this this infinite stage. Then it must have gone to 0 already at a finite stage by this compactness argument that we had in the previous video. But the whole point about how we constructed xj was xj was constructed so that U doesn't go to 0 in the complement of xj. So this is a contradiction. So this shows that this element U that we imagined at the beginning cannot exist, and therefore that Sn less x is acyclic. So there's one sort of slight point here. So we need to say something about the H0 of this. We'll notice that X is contractible, Sn is not contractible. So X is certainly not equal to Sn. Sn less X is okay, so we do need to know that this Sn less X is non-empty, but that's true because X is contractible and Sn isn't, so the Sn can't be the same as X. Okay, so that means that you've got at least one path component here, and therefore your P lower star from here to Z is surjective, and then if you look back to the rest of the argument, that's going to show us that this P lower star is actually injective as well. So this proves that the complement of a ball is acyclic, and that's a key step for the generalized Jordan curve theorem. So now the next thing is to consider the complement of a sphere instead of a ball, which is what we'll do in the next video.